All right, today we're going to be talking about log functions and how we go between logarithmic and exponential functions. So we're really going to just kind of go through the basics of logs. And so this is kind of just like what a basic log is, and reminding ourselves that a common log is a log base 10. And then we're going to be dealing with natural logs. So we're going to be talking about something and how we can go into exponential form in here just a minute. So let's talk about here. For a long time we had equations like this where we said 3 to some exponent equals 81. And we said, well, what's x in this equation? And the best way was to kind of guess and check. Probably grab a calculator and say, well, 3 squared is 9, 3 to the third is 27. Oh, 3 to the fourth is 81. So we could say x must be a 4. But now, what if I said 3 to the x is 100? There's where you're like, well, then x has to be a decimal. Because 3 to the fourth is 81, 3 to the fifth, oh gosh, what is 3 to the fifth? Higher than 100, I would think. 3 to the fifth is 243. So we know we're closer to the 3 to the fourth, and so you can kind of estimate. And so you know guess and check isn't an option, so we're going to have to do a different method. And the method we came up with is we found, and they kind of would guess and check for a long time and figure it out, but they found that a much quicker option is called the logarithmic form. And so the log is just a process, or kind of like a formula kind of that you apply to a value. Okay, so when someone says 3 to the x, we said, well, there's actually a mathematical operation we could do that says we take it log base 3 of 81 equals x. Okay, so let's talk about how I could figure this out. Or how I can kind of write and go between both forms. So let's look at this. So if I look at this, I would say log of x, and what I think of it in my head is I think of we're going to interchange the two values around your equal sign. Log of x equals y, we're going to make it base b to the y power equals x. Okay, and we'll talk about what these other things are in a minute, but let's see if we could do this. So this problem, it's a true statement. I just want to make sure you understood that we're dealing with a true statement here. That log base 27 of 3 is 1/3. So all I would need to do to write it in exponential form is to say, well, that means that 27 to the 1/3, I switch these two around, must equal 3. And that answer is true. It's just a true statement. I think the biggest problem is students want to switch this around, or they want to solve it. There's no solution. It's just taking a true statement and writing it in a different way. Here, this other true statement is 16 to the 1/2 would equal 4. Let's do some more. We'll go through and I'll give you the answers to 1, 2, and 3 in just a minute, but let me go through and I want to go through some more of these exponential forms. This case, it would be 4 to the third equals 64. In this one, 2 to the fifth equals 32. Go ahead and pause it and see if you're getting the same answers. 9 to the 1/2 equals 3. These are just like, yep, they are. And so now here you're going to see magically the answers to the top row. So those are just a review of stuff we covered in chapter 6, and I kind of wanted you to take a minute and review it. So just like we need to know how do we go from logarithmic form into exponential form, we need to say, well, what if you're in exponential form? How can you put it in logarithmic form? And again, the idea is then just you add a log. And so now it's log base 3. 3 was always our base of 81 equals 4. So it always equals the exponent. Now it's log base 5 of 125 equals my exponent. Here, log base 7 of 49 equals 2. So evaluate the following logs. Remember, this is like equal sum exponent, all right, equal sum x. So you would say to yourself, 9 to the x power equals 1. What exponent would you always get 1 for the answer? And the answer is that 0. When x equals 0, exponent is 0, you get 1 for an answer. In this case, 1 over 27 to some exponent equals 3. All right, this one's a little harder. Because usually what we do is we say, well, if we only have the same base, then we can kind of compare their exponents. So 27 is really 3 cubed. So I have 1 over 3 cubed equals to the x power equals 3 over 1. And that leads to, how do I get that in the numerator? Well, if you remember from the last chapter, it's a negative. So 3 to the negative 3x equals 3 to the 1. So hopefully it kind of follows that, hey, these two have to be equal to each other. So if negative 3x equals 1, then x equals negative 1/3. We'll be going over more problems like that, all right? Here's another one. 16 to the x must equal 4. Well, it's the square root of 16 that equals 4. Square root in an exponent is shown as 1/2. Here we have 4 to the x equals 1 over 16. Again, what makes it go in the denominator? I know 4 squared is 16, but 4 to the negative 2 makes it go into the denominator, would be 1 over 4 squared, which is 1 over 16, so x must have equaled a negative 2. So logic can really help out a lot. Here, 81 to some exponent equals 3. I know now it's the 4th root, okay? Another way to think of this is 81 I figured out just before was 3 to the 4th. So I still have that x there, equals 3, all right? So 4x must equal 1, x equals 1/4, also known as the 4th root. Natural log of e is 1. Okay, so e. We were dealing with log, and there's these types of problems that usually had to do with exponential growth and continuous growth, and we kept having this value come over and over again. It was like 2.7 something else. And they said, oh, it always comes to this, always comes to this. And so they gave it a value so that they can just work with it, and they called it e. So if you find e on a scientific calculator, you're going to see e to the first power is 2.7 something. It's a lot like pi. So log base e is shown as, or they said, well, let's just do a shorthand for that because we're using log base e all the time. And they did a shorthand for that, and that was ln, for natural log. Now you're going to say to me, well, no, ln, natural log should be nl. Well, it was actually decided that it should be like this by a French mathematician, and in the French language, now natural log was actually spoken as log natural. And so that's why natural log is ln. So the log base e, so this is basically ln. So this is saying the log base e of e is some value, okay? Well, e to what value equals e? Oh, e to the first, that's why. It does help just to memorize natural log of e is 1, all right? That helps because that's actually used a lot to solve some problems. All right, sometimes we can't figure it out. I couldn't tell you what 5 to the x equals 20 is, all right? But we do have a workaround. We do have something called the change of base formula. We found out that the exponent will always equal the log base 10 of the outside divided by the log base 10 of the base, okay? So log of 20 divided by log of 5. And you could put this into your calculator. The only thing you have to be careful of to make sure you have parentheses around the log base 20 and the log base 5. Now you're going to get an estimation here. It's not going to be an exact. So I'm going to go on my calculator. My log there is automatically log base 10. So log base 20 divided by log base 5, log of 5. I get 1.86135. And I'm going to use this to show that, hey, it's approximate. I know I'm going to round it at some point. This one here, since 3 to the x equals 60, I know that my x equals log of 60 divided by log of 3. If you ever are told, I want an exact answer, or if you just don't have a calculator with you, it is perfectly good. In fact, I'm pretty happy if you leave it at log base 60 over log base 3. All right, that is an exact answer, and you could leave your equal sign as they are. You don't have to do the little curvy equal sign. This case, again, I'm going to think of it as 8 to some exponent equals 205. And therefore, my exponent would equal the log of 205 over the log of 8. I'm going to leave it in exact. All right. So now, another thing that we work on with logs and we found very helpful is this idea that logs have some unique rules of how you can expand and then condense. So we're going to first deal with expand. And expand says, hey, we can deal with multiplication, and we actually change it into a kind of a type of addition. So right here, I really have 3 times my x to the 4th right there. So to expand it, actually it is an equal sign. I should have put down an arrow, sorry. You can say that really we're going to expand it into 2 log base 2s. So it's going to be log base 2 of 3 plus log base 2 of x to the 4. So I want to point out a couple things. I had to rewrite log base 2 twice now. So in order to expand it, you're saying if you just took the log base 2 of this value and then took the log base 2 of this value, then it expands out, and you can kind of expand it out. You have to have, so I took one log base 2 and I expanded it to 2. Okay? The other thing you can do, another rule, is that exponents can become coefficients. So I can rewrite this as 4 times the log base 2 of x. So this is the same value, the same thing we started with, but what we call expanded. All right? So it's important to remember that to expand it, you have to rewrite the word log several times. Oftentimes, exponents become coefficients of the word log. In this case, natural log of 5x divided by 3. Well, if multiplication here turned into addition, what do you think division is going to turn into? Turns into subtraction. So this equals the natural log of 5x minus the natural log of 3. And some of you might catch that, hey, this is actually multiplication, so can't we split that up? And yes, you can. That can be split up into the natural log of 5 plus the natural log of x. And then we have the natural log of 3. Now this one's kind of easy to see the benefit of this, because I can plug this into my calculator and get an answer out for what the estimation for the natural log of 5, estimation for natural log of 3, and the only one I don't have is what this x is. So I can get closer to what the value should be by doing this expanding. The log of 6, base 6 of the square root of x divided by 4. First of all, I would take the division and I would make it log base 6 of square root of x minus log base 6 of 4. Well, this square root of x, we really can show as x to the 1/2. Remember how square root is like 1/2? And then that exponent can become the coefficient. So really, this is my final problem. Sorry, my board is going a little crazy. Minus log base 6 of 4. And in math, we love to go forwards and backwards. So that's what we're going to do here. Now we're going to take something in expanded form, and we're going to put it into condensed form, or we're going to try to condense it. All right? So let's first look at the first one. First thing I do is I do what's backwards. Like here, the last thing I did is I took exponents and I moved them down. So the first thing I look for is what could be an exponent. In other words, what's a coefficient? So I would go through here, and I would say, hey, this too can be an exponent now. That's my first step. Then I look for addition and see how can I change it into multiplication. So log base 3 of x squared now times 5. And we could have written that as 5x squared. I don't really care. You could leave it like that as well. Next problem. I'm going to take a coefficient, what's in front of the word natural log, and make it an exponent. I'm going to take this coefficient and make it an exponent. Then I'm going to change addition into multiplication. So natural log of 16 times x to the 3rd, and the subtraction into division, divided by 2 squared. I could combine and make it look a little prettier. Natural log of 16x cubed over 4, and even prettier, natural log of 4x to the 3rd. All right, let's look at this one. I'm going to make this an exponent. Addition turns into multiplication. Log base 8 of 6 times 3 squared really equals log base 8 of 6 times 9, 54. One last problem here. All right, exponent, exponent, kind of have to think of it like that. And there we go. I'm going to change this. We have now log of 2 squared. I'm going to make it 4 times 1/4 squared times 4x. Why they didn't split this up, I don't know. All right. 1/4 squared, this would be really 4 over 16 times 4x over 1. These all cancel out. This would be a 16/16. So my answer in the end is really log of x. Much simpler. Okay, let's keep going. The last thing we're going to be working on is how we can look and make it have a similar base. If the bases were the same, we can reduce. So in this case, this log, I'm going to look at 28 first. I can just ignore my log base 6's here. So I could just solve the problem. What is 5x plus 8 equal 13. And how do I solve that? Okay, it ends up in the end, 13x, sorry, x would equal 1. But so like for this problem, I could say this 27 is really 3 cubed. I know 27 is 3 cubed. And then we have x plus 3 is over here still. And that equals 3 to the x plus 1. Well, I can ignore the bases because my exponents would have to be equal to each other. X plus 1 would have to equal 3x plus 9. All right, 2x would equal a negative 8, x would equal negative 4 for that problem. In the E, couple different things I could do. Most common one is to take the natural log of both sides. Because now exponents come out in front. And this is kind of a cool trick because remember before when I said you just kind of need to remember that natural log of E is 1? This is like times 1. We can ignore it. So now we have that negative 2x equals natural log of 5. So x would equal natural log of 5 divided by negative 2. And actually I'm going to leave it there. You can find an estimated answer, but you could also leave it. Let's look at 29. I'm going to write 8 as 2 cubed. Oops, 2x plus 2. I'm going to write 16 as 2 to the 4th. So now I know that 6x plus 6 should equal 4x minus 20. All right, so 2x should equal negative 26. X must equal 13.